So, next topic, circular measure. So this is all about circles, as the name would imply, and we're going to mainly deal with things called arc lengths and sector areas. But the first thing that is sort of the step up from IGCSE is the introduction of the radian. Now this is a unit of angle, and you may be very familiar with degrees, which is 1 full revolution is 360 degrees. But this was invented very arbitrarily. Like, this number of 360 wasn't chosen for any mathematical reason apart from has a lot of factors. That's literally pretty much the only reason why it was chosen. Radians is, however, much more natural in a way and is much more used in a high level maths and physics. And so what is the actual definition of a radian? The proper definition is angle subtended at the centre of the circle by an arc that is equal in length to the radius. Okay, what the heck does that mean? So let's draw a circle and just imagine an arc of, well, this is our radius, a bit longer than the radius unfortunately if I shorten that, but, and then I take that and I just roughly do an arc, draw along the border of the circle that is roughly equal in the radius. We'll call this R, we'll call this R. What this word here means, subtended, means draw straight lines from the ends of the arc. That's where that word arc comes in. You draw straight lines from the ends of the arc and you draw it to the centre. And then you just get the angle formed by those straight lines. Here, this is 1 radian, roughly. So the next question we can ask is, well, how many in 1 full revolution? And that's this, how many radians we can fit in the whole circle is simply equal to how many radii can we fit on the whole circumference. And already you'll know, you'll be thinking, circumference equals 2 pi r, divide both sides by radius. How many radii can you fit in the circumference? 2 pi r over r, and that gives you 2 pi. So that tells you that there are 2 pi radians in 1 full revolution. Therefore, 2 pi radians equals 360 degrees. So radians will equal 1 radian equal 360 over 2 pi degrees. And that's 180 over pi degrees. So to go from radians to degrees, conversion factor will be multiplied by 180 over pi. Then to go from degrees to radians, you multiply by pi over 180, because division is the same as multiplying by the reciprocal. And the way I kind of remember that conversion factor is you'll often see, you'll know that in degrees it's not very common to have it in terms of pi. So in order to get radians, which sometimes can be, which most of the time is in terms of pi, you have pi on the numerator. It's almost like you're adding the pi to the term. But with radians to degrees, it's almost like you're trying to get rid of the pi. You divide by pi, if that makes sense. So now you know the relationship between radians and degrees. And now we can actually start applying this to two things: arc length and sector area. And just up here I'll draw another circle. If we do this line here is called a chord, and this here, if it goes to the centre, this is a radius. Then this is another radius, so this is thing on here is called an arc. This is actually the minor arc, because it's the, you could also have an arc over here, which is your major arc. Now this thing here formed by that chord is called a segment, and this thing here is called a sector. So the two things we want, we're going to use radians to find out is the area of the sector and the length of arcs. So arc length. As you can probably tell by now that it's going to seem pretty obvious, arc length, and this is symbol S. The ratio of arc length to the circumference, 2 pi r, is going to be equal to the ratio of the angle of that, well, the angle subtended by the arc, so our theta, divided by the full amount of degrees, which is 360 degrees. But we're talking radians now, so we change this to 2 pi. So then if we want to isolate the s on its own, we multiply 2 pi r by theta over 2 pi. 2 pi's cancel out, so we get s equals r theta. Seems very easy to remember, and it is very easy to remember. Sector area, we'll just give it the symbol A. And it's very similar, we're going to derive the formula in a very similar way. You should notice that if you've drawn pie charts before, the area of that sector divided by the full area of the circle, which is pi r squared, that ratio is going to be the same as theta over 360 degrees, which, as we know, needs to be in radians, so we change that 360 degrees to 2 pi. So now A will multiply out times, and we'll write this as kind of 1/2 times. So those pi's are going to cancel out, and we're going to be left with half r squared theta, our second formula. It's very simple, very easy. Now in questions, those will be the two formulas you will need to use in circular measure. However, in order to solve some of the problems, you may have to use some other formulas that you would have learnt in IG. Most important ones would be your triangle areas. and that can either be half base times height or half AB sine C. And remember, just your example triangle, if this is your C, this will be your lowercase a, your lowercase b, lowercase c, and then this would be your b, this would be your a. And you could do half CB sine A, half AC sine B. It doesn't really matter as long as you're getting two sides and the angle in between those two sides. And another one you want to remember is with your right angled triangles. A, B, C. Obviously A squared plus B squared equals C squared. And also, additionally, you need to remember SOHCAHTOA. So this is also in a right angled triangle. So if we label our theta here, we know that the side opposite the right angle is the hypotenuse, then the non-hypotenuse side adjacent to the angle is adjacent, and the other one is opposite. And remember, sine of theta equals opposite over hypotenuse. Cosine of theta equals adjacent over hypotenuse. And tan theta equals opposite over adjacent. And additionally, if sometimes you may get a question requiring you to apply this, either of these rules, you could have the sine rule or the cosine rule. And again, I will label this is A, B, C, making this A, making this B, making this C. Sine rule states that sine A over A equals sine B over C, sine B over B equals sine C over C, or the other way around, e.g. A over sine A equals B over sine B equals C over sine C, etc. Then for cosine rule, it would be, there are several rearrangements, but you could have C squared equals A squared plus B squared minus 2AB cos C. And likewise, if you rearrange this a little bit, you could have B squared equals A squared plus C squared minus 2AC cos B, etc. And the other one is, if you wanted the angle, would be perhaps cos C equals A squared plus B squared minus C squared over 2AB. You may be expected to use those two rules in questions in circular measure, because this is pretty much geometry in AS. And then one thing you may want to know is also trapezium. A plus B over 2 times H. It's like you are averaging A and B and then doing base times height, if that makes sense. Alright, fundamentally that's what you need to know for circular measure. There will also be a video just going through some basic problems of circular measure later on.